Hello everyone and welcome to your Chem 113 review on specific heat and heat capacity. My name is Jason and I work for the ASU Tutoring Center. Now, let's go over some definitions before we jump into these problems. We kind of need those for this problem. So what is heat capacity? Well, heat capacity is, if you look at an object, it is the amount of heat. And again, we can think of that as sort of enthalpy, right? The heat energy, amount of heat needed to raise its temperature by 1 Kelvin. That's what that K is. What is a Kelvin? How exactly do we calculate a Kelvin? Well, Kelvin, it's a unit of temperature, and how you calculate it is you just look at Celsius. So if you have degrees Celsius, you take that, you add 273.15, very specific number, and that's how you convert it into Kelvin. So if you have 30 degrees Celsius, that corresponds to 303.15 Kelvin. All I did was I added 273.15 to it. Like, why would we do that? That's such a strange thing to do. All we're doing is shifting all the Celsius units over to Kelvin units. And you're entirely correct. The reason we have to do that is Kelvin is sort of the standard temperature unit for chemistry. So just like the meter is the standard for distances, just like the liter is the standard for volumes, we have Kelvin being the standard for temperature. So a lot of the equations we use and work with and formulas that we know from chemistry require it to be in Kelvin. Okay, some things to note though. If we were to try to find a change in Kelvin, so that's like your final Kelvin, your final temperature in Kelvin minus your initial temperature in Kelvin, you want to find that change. Well, if we were to convert, let's say final Kelvin minus initial Kelvin, if we were to convert these kelvins into degrees Celsius, this would be like your final degrees Celsius plus 273.15. And this would be like your initial degrees Celsius plus 273.15. And if we distribute this negative, you'll realize these cancel out. So the change in Kelvin actually equals the change in degrees Celsius, because this is sort of like an additive property. Since you're just shifting everything over, like the distance between the Celsius here, if you're just shifting everything over, it's the same distance over here in Kelvin world, right? So that's going to be a useful thing. If you're trying to find the change in temperature, you can leave it in terms of Celsius, because that change in temperature in terms of Celsius is the same as the change in temperature in terms of Kelvin. So that's just a useful little tidbit for you. Okay, let me go ahead and erase this real quick, and we will continue our various discussions on definitions. Okay, so heat capacity is the amount of heat needed to raise its temperature by 1 Kelvin, whereas this term, specific heat capacity, this represents the heat capacity, so the amount of heat needed to raise this temperature by 1 Kelvin, but it's the heat capacity of exactly 1 gram of whatever substance you're working with. So it has a little more specification to it, right? Like if you have a lot more of something, it'll probably take longer to heat it up, right? Like if you've got like chicken and you're trying to heat it up on the stove and you just trim some of the fat off and that's it, and you just have like this gigantic thick chicken breast, that's going to take a little bit. But if you slice it up a little bit, flatten it out with your little mallet, and then throw it on the stove, that's going to heat up a lot faster. Okay, just because you have less of it to heat up. So specific heat capacity a lot of times is more useful because it takes into account that the amount of substance you have changes the amount of heat you need. Okay. Cool. So there is a formula that relates specific heat capacity and like heat. And I will show you what that formula is. It is a very famous formula. It is Q. That's not a Q, that's a G. It is Q equals MC delta T. A lot of people memorize this formula as the MCAT formula. It looks kind of like MCAT. You know, the MCAT, the thing that people take to get into med schools. Here, Q represents sort of just the heat, okay, or the enthalpy, right? Heat energy. Enthalpy. M is the mass of your object. C, this is the specific heat capacity. And delta T is change in temperature. Okay, which again, we would technically have to calculate it in terms of change in Kelvin, but as we mentioned earlier, change in Kelvin is the same as change in degrees Celsius. So let's sort of, we're trying to solve for C in this first one, right? Oh, never mind, we're trying to solve for Q, my bad. We're trying to find the amount of heat, we're trying to solve for Q. So we can plug in the information that we have. Do we know the mass? Well, yes, it's 250 grams. So we're just gonna plug in 250 G. Okay. What about the specific heat capacity? Well, the specific heat capacity was given to us. The specific heat of water is 4.181 joules per gram Kelvin. That's an important number to know. You don't necessarily need to know it to the 1,000th decimal place, but it is an important formula to know. So that's 4.181 joules per gram times Kelvin. And then the delta T, the change in temperature, that's something we would have to calculate, right? Our final temperature near its boiling point is 98 degrees Celsius, whereas our initial temperature was 22. So that tells us that that change in temperature would be 98 minus 22, which comes out to 76. And again, although these are in Celsius, we can look at this change in temperature as a change in Kelvin, because it's going to be the same. So delta T is 76 Kelvin. And I mean, the first thought I thought was, when I saw the 250 grams, I immediately wanted to convert it to kilograms, right? Because kilograms are sort of the standard mass unit in chemistry. But you can decide if you need to or not based on the specific heat. The specific heat, remember, is the amount of heat required to raise this temperature by 1 Kelvin if you have exactly 1 gram of substance. So because this unit down here in your specific heat is grams, you'd want to leave this in grams as well, so they would cancel out. And then same thing here, these kelvins cancel out, and all you're left with is joules, which joules is a measure of energy, so it makes sense for it to be the unit of heat here. And when you do that multiplication, you get 7.9 times 10 to the 4th joules, which if we do a unit conversion to kilojoules, which is very common, we get 79 kilojoules. So that is how much heat energy you would need to warm up 250 grams of water from 22 degrees Celsius to 98 degrees Celsius. That's how much heat energy. So that's cool. Now you know if you take 250 grams of water, put it on the stove at 22 degrees Celsius, and you heat it up, you know exactly how much energy is being transferred from your burner to the pot to heat up your water. And then from the pot to your water to heat it up. Isn't that pretty cool? It's pretty cool. Okay, so 79 kilojoules. Good stuff. That was part A, or part 1. Part 2 is saying, what is the molar heat capacity? Okay, so that's another new term. We have heat capacity, specific heat capacity, molar heat capacity. So molar heat capacity is the heat capacity. So again, heat capacity being the amount of heat needed to raise this temperature by 1 Kelvin. But instead of like specific heat, where it's the amount of heat needed to heat up exactly 1 gram of the substance, this is to heat up 1 mole of the substance. So heat capacity of 1 mole of your substance. Okay. So we can get this actually from our specific heat of water. So looking at our units for specific heat, it's 4.181 joules per every 1 gram times Kelvin. So essentially we want it to be the same kind of units, except instead of a grams here, we want it to be a mole. So how are we going to convert this gram into mole? Well, we're talking about the molar heat capacity of water. So if we have the molar mass of water, we can convert grams to moles. And we do know the molar mass of water, right? We can find it using the periodic table. It's 18.02 grams of water for every 1 mole of water. That's a 1. I try to write it in that way, so it's distinguishable as a 1. And by doing it this way, our grams cancel out, and we get joules per mole Kelvin, which would be the units for molar heat capacity. So all we have to do is multiply by the molar mass of whatever your substance is. And this gives us 75.2 joules per mole Kelvin. So following units and watching the units is an incredibly powerful tool in chemistry and in most science. It's very beneficial. Highly recommended. Okay, that's all for this question. As I mentioned, I work for the ASU Tutoring Centers. So if you want more information about the free resources we offer on all 4 major ASU campuses and online, check out tutoring.asu.edu/content/tutor-search. By going to this link, you'll be able to find a tutor on your campus or online that will be able to help you with your specific course. Thank you for watching, and I hope you have a fantastic day.